Hello guys. So today we are going to understand what is PCA, what is covariance, eigenvector, eigenvalues, how these all things are linked together, how PCA makes sense. We will talk about all these things. So guys, my name is Mohit. I have over 20 years of industry experience with IBM, MX, NIT, NCR corporations, etc. Recently, I have been exploring learning, deep learning, transformers, LLMs, and it fascinates me so much that I completed a diploma from Texas University. Now I'm excited to share these powerful concepts to you. Okay, so why PCA? In machine learning, data is power, but only when we can make sense of it, right? So most real world data set contains many features, which is also called dimensions or variables. Sometimes these data sets can easily have hundreds or even thousands of such features. While this may sound beneficial, it actually creates a major challenge for machine learning algorithms. As the number of features grows, model becomes slower to train and it requires more data to generalize well, and it struggles to identify meaningful patterns. This challenge leads us to fundamental problem known as the curse of dimensionality. All right, so curse of dimensionality. If you see this, if we have some data in one dimensional space, it is close to each other. But if we add some more dimension, if we add one more feature in that data set, then the data points will be far away from each other. And if we increase it more, then you can see that the data becomes more sparse and the distance between each point increases. This makes it harder to find patterns or relationship in the data. And this curse of dimensionality, it refers to the phenomenon where the difficulty of analyzing data increases as the number of dimensions increases. So, how can we handle this high dimensional data? One way to handle this high dimensional data is feature selection. This is a straightforward solution. Simply remove one or some features and train the model using fewer variables. But this approach has a big drawback. Important information may be lost and model accuracy may decrease. So instead of discarding features, we need to find a way to compress information without losing. And this is where PCA, principal component analysis, comes into the picture and helps us. All right, what is PCA? PCA is principal component analysis. Okay, this is very interesting. Principal component. We will try to see what is principal component means. But before that, PCA. PCA, it is an unsupervised algorithm that reduces the number of features in the data set while preserving as much as the data variance as possible. So this is something important. We are trying to preserve the data variance. What is variance? Why we are trying to preserve the variance? Variance helps us to find the pattern in the data. If we don't preserve the variance, we won't be able to find the true pattern of the data. So basically patterns or relationship in the data are often defined by how different variables change relative to one another. If there is no variance, all data points are the same or very similar, which means a model cannot find any meaningful relationship or differences. So the objective of PCA is to apply some transformation to the features to extract new features. So it is not discarding any feature, it is trying to do some transformations and trying to find new features without losing the feature importance. And then by doing so, it will minimize the number of features because with the lower number of features, it can extract the same variance or same information. All right. So in short, we are PCA is trying to reduce dimensions without losing what makes the data informative. Now, Let's try to understand the geometric intuitions behind it. So let's imagine a data set, house size, number of rooms, and there is a target variable which is house price. Based on house size or number of rooms, we are trying to predict, predict the house price. This is a very small data set. We have only two features and there is only one target variable. And PCA does not care about this target variable. The goal is to only reduce the feature dimension. We are only focusing on these house size and number of rooms. Now, if we try to see the pattern between house size and number of rooms, we find that there is some relationship. And that is what PCA will try to find some way to reduce this dimension. So for simplicity, we just kept it as 2D, and we'll try to see if we can make it 1D. Again, if we simply drop the number of rooms as part of feature selection, we'll lose all variation along that axis, right? But PCA does something smarter. Now, if we try to see the variance of this data for this house size, we see that, okay, this is the variance of the data for the house size, and this is the variance of the data for number of rooms, which makes sense. Okay. Okay, now what PC will do? Okay, we understand there is a variance, but how PC will reduce the number of dimensions? So what PCA does, PCA try to find a new axis, or I should say new axis. It will try to find this axis, which is, house size, dash, but it won't be a house size, it would be something else. So it will try to find a axis which will try to capture the variance as much as possible. Okay, this new axis still captures the maximum variance if you see. And the other axis would be perpendicular to this axis, obviously. Now, if you see, this axis is still capturing the variance. And this axis is also capturing some of the variance. And that is what we wanted. The new axis created by PCA, if you see here, are called PC1 and PC2, principal component 1 and principal component 2. Now, if you see that, we should be able to drop this new axis, new dimension, because it is not capturing much of the variance. There is one axis enough to capture all the variance. If we drop this dimension or drop this feature, we won't be losing much of the information, much of the variance, because it is very low, right? And that's what the all the reasoning behind PC. It is trying to find the lower features, lower number of features using which it can capture the maximum variance. And how it happens? This is where eigenvector and eigenvalues helps. Eigenvector with the highest magnitude will be our best principal component. So this is our best principal component which will capture the maximum variance. Yeah, we will try to understand what is eigenvector and eigenvalues, but I'm just trying to make that point that eigenvectors are the one which, which captures the maximum variance for PCA. All right, let's take a detour and try to understand what is eigenvector and eigenvalues. So eigenvectors are a fundamental concept in linear algebra. It's playing a pivotal role in various machine learning and data science applications. If we look into this, eigenvector V of a matrix A is a vector that does not change direction when multiplied by A. What does it mean? If you see it, we are trying to apply some linear transformation on this eigen on this vector, and if the vector direction does not change with this linear operation, then that vector is called eigenvector. If you see this, this is our matrix, and we are applying this matrix to this vector, and the vector direction is not being changed. It just its magnitude is getting changed, right? That is the reason it is called eigenvector. Let's try to see it through some graph. All right, this is a very interesting visualizer for this linear transformation. Let's say this is our vector, and we are trying to apply some linear transformation on it. Okay, this is our matrix, and we are trying to apply this linear transformation to this vector. And if you notice here, if we apply this transformation, the direction of this vector gets changed, right? See this? Maybe we can move it to somewhere else. Let's say this one, or let's say this one. And if we see the transformation, see the direction and the magnitude gets changed. But if we find some vector for this matrix for which direction does not change, then that would be our eigenvector. So let's see some eigenvectors for this one, right? So let's see, this was the one, and if we apply this, see, these are two are eigenvectors. Okay, so now if we put our line, or if we put our vector into this direction, I'm just trying to make it exactly 1 1. Okay, let's say it is almost 1 1. Okay, now if we apply to this linear transformation to this vector, notice this direction is not getting changed. It's just the magnitude of this vector is getting changed. And that is what our eigenvector is. I hope this makes sense. You can also give it a try and try to understand this eigenvector. So basically, again, what we are doing, we are trying to find a vector for a given matrix. When we apply some linear transformation to the given vector, if its direction is not getting changed, then that vector is called eigenvector. All right, back to our slide. So we understand this part. Now let's see what else. There are a few other things about PCA. Let's come back to our PCA again, right? So PCs are calculated based on decreasing order of the variance, right? So we'll notice that the variance of PC1 is always greater than variance of PC2. So basically, PCA is trying to find the principal component in such a way that the first principal component is capturing most of the variance, and then PC2 is capturing lower than that, but more than other principal components. The other interesting concept is, if we while calculating this, while finding this PC1 and PC2, we ask PCA, we need to convert data set from 5D to 3D. So we need only 3 dimension. So it will only consider PC1, PC2, and PC3. Or if we ask PCA to convert data set from 5D to 4D, we only need 4 new features, and that's the reason we will only consider PC1, PC2, PC3, and PC4. Now, the question is how to get eigenvector and eigenvalues. And this is where covariance matrix helps. Okay. Okay. I know it is a bit confusing. We'll understand each and everything around it. Okay. We understand what is eigenvector and eigenvalues, but how this covariance matrix we will calculate, or how we'll get eigenvector and eigenvalues from covariance matrix. Okay. First, understand what is covariance. Covariance is nothing. It's a measure of how two variables change together. It is also, if you know correlation, correlation is also the same thing. It measures how two variables change together, but correlation gives both direction and strength of a linear relationship, but uh, covariance only gives direction, not any strength. Okay, just for your information. But let's come back to this covariance. So if you see this, this is a case of negative covariance, which means that the data points move in the opposite directions. This is a positive covariance where data points move into the same direction. If it is getting increased, this is also getting increased. And this is a case of zero covariance. Sorry, so it should be zero covariance. My bad. All right, so it gives you only direction covariance, right? And unlike correlation, covariance values do not have any limit between -1 and 1. All right, there is one more point which is very interesting, that while it shows the trend, its value is hard to interpret because it is affected by variables scale. So it depends what is the scale of these x and y. Though the relationship of this is stronger than this, but there is a very much possibility that it is having high covariance. So don't get confused. If there is a high relationship, that doesn't mean it would be having high covariance. So it could be wrong to conclude that there is a high relationship between variables if the covariance is high. And there's a formula to calculate covariance by using this data point. So we can use it to calculate the covariance. Now, what is covariance matrix? Covariance matrix provides us both spread and the orientation. It provides variance and the covariance of our data. So if we look into this, if there are two data points x1 and x2, right? So the covariance matrix would be like this: covariance x1 x1 and covariance x1 x2, and then x2 x1 x2 x2. And then when we see covariance x1 x1, which means it is a variance of x1. Similarly, this one is variance of x2. So this is our covariance matrix. Now we understand what is covariance matrix, right? Covariance matrix gives us the variance and the orientation of the data. Now the question is, how do we find eigenvector from covariance matrix? Okay, let's say if we can calculate covariance matrix for given data set, how do we find eigenvector? If we represent the covariance matrix with a vector and its magnitude, we should simply try to find the vector that points into the direction of the largest spread of the data. Oh, whoa, whoa. This is very technical. This is hard to understand. Okay. So if we come back to this diagram again, right? So covariance matrix is able to provide us everything about this pattern, right? It is able to let us know the variance of the data. It is able to provide the direction of the data. The only thing is it is a matrix and we need to find these vectors PC1 and PC2, right? And that is what we can use this eigenvector and eigenvalues formula to find those vectors. So basically in this one, this matrix is our covariance matrix. Now, if we want to represent this covariance matrix A with a vector and its magnitude, we need vector that point in the direction of the largest spread of the data. Okay, and that is our eigenvector. This is what we understand, right? If we can find a vector which does not change direction but is and gives the largest variance, that would be our eigenvector, and that is what we are trying to find. This is all mathematical proven. You do not need to worry about how this has been defined, but the point is, if we need to represent this covariance vector into a vector and magnitude, eigenvector is the one which would give you the vector with the largest spread of the data. All right, so this is what it is. It is mentioned. So eigenvector of a covariance matrix is a vector which will give you the largest variance in the same direction. All right, now see how PC works. First, we standardize the data. We center the data around zero and scale features. So that is the very first step. We calculate the covariance matrix and try to understand how features vary with respect to each other. We can do that using the formula. And then using that covariance, we can easily find the eigenvector and eigenvalues. Again, using the formula. We sort the eigenvectors because we need the PC1 with the largest variance and then PC2 with the next largest variance and blah blah. And then finally we project the data onto the principal components. And that's how we uh, the dimensions of the data set get lowered down. So the conclusion is PCA is powerful because it reduces dimensionality, it preserves important information, it improves model performance we have seen, and it helps visualize high dimensional data. So instead of dropping features like feature selection, it reorganizes information in a smarter way. So now let's quickly go to the code example and see how PCA works. Okay, now let's see some example. Okay, so we import some libraries, Panda, PCA, plot, etc. There is some data. I have wine.csv and we distribute the data set in X and Y where X is having all the features and Y is the target variable. And if we look into this data, there are so many features, around 13 features we have, 13 or 14 features we have. First, as we know the steps, we standardize the data, we apply PCA, and we while applying PCA, we say that okay, we need only two principal components. Okay, we transform the data and then we try to create a principal data frame and final data frame. Okay, if we see this final data frame, we have this principal component 1 and principal component 2. There are only two components of it. And if we try to, and there is a way to see the explained variance ratio for this PCA. So explained variance per component is there are two components of 0.36 and 0.19 and the total explained variance is 55, which is not good though. It should be somewhere 95, 99. But I just wanted to show you. Maybe we need to increase the number of features to capture more variance. But this is how we can reduce the number of dimensions and we can see how much variance it has captured. Okay, let's go back. Okay, thanks guys. That is all about PCA. Please let me know if you have any further questions. I would be happy to answer that. Thank you.